China has spent the past decade pursuing a single strategic objective: the ability to manufacture advanced semiconductor chips entirely within its own borders, free from Western control. The reason is simple. Without domestic chips, the People's Liberation Army cannot guarantee that its most lethal weapons will work in a crisis. Hypersonic missiles, intercontinental ballistic missiles, stealth fighters, and autonomous drone swarms all need processors that cannot be remotely disabled or cut off by sanctions. Now, after years of crash investment and despite sweeping U.S. export controls, China has crossed that threshold. SMIC is producing 7 nanometers chips at scale using only older DUV tools, no EUV machines required, and according to multiple supply chain analyses, those chips are already flowing into next-generation PLA systems. The result is exactly what your title promises: a year-over-year increase in lethality that the Pentagon cannot stop. Because the traditional choke points, ASML tools, TSMC fabs, and Western software have been bypassed by a parallel sanctions-proof ecosystem. Semiconductor Manufacturing International Corporation proved the skeptics wrong in 2023 when its 7 nanometers Kirin 9000S processor appeared inside Huawei Mate 60 Pro. Using only older ASML DUV immersion tools and a technique called Self-Aligned Quadruple Patterning, SMIC fabricates transistors dense enough for 7 nanometers logic without a single EUV scanner. By late 2025, SMIC had moved its 5 nanometers class N+3 node into pilot validation, with volume production targeted for 2026. This engineering feat does not match TSMC efficiency, but it delivers functional chips that are already being integrated into dual-use and military systems. The physical barrier that Western export controls were designed to create has been bypassed through sheer engineering intensity and state-backed investment. China's current advanced node capacity is estimated at roughly 20,000 wafer starts per month in early 2026, with most of that dedicated to 7 nanometers and a small pilot share for 5 nanometers. According to Nikkei and TrendForce, Beijing aims to boost 7 nanometers and 5 nanometers output 5-fold to 100,000 wafers per month within 2 years, and then add another 500,000 wafers of monthly capacity by 2030. SMIC plans to double its 7 nanometers output in 2026 alone, while Huahong Group's Shanghai Huawei subsidiary is preparing an initial 7 nanometers pilot line expected to reach several thousand wafers per month by the end of 2026. These targets are ambitious, but even reaching half of them would give China more advanced node capacity than the entire US trusted foundry ecosystem. For military applications, where volumes are measured in thousands rather than millions, this capacity is already more than sufficient. The price of achieving 7 nanometers without EUV is brutal by commercial standards. Industry analysts, including reports from the Financial Times, estimate that SMIC yields for complex 7 nanometers AI chips range from 20 to 40%, far below TSMC 85 to 90%. Its 5 nanometers pilot yields are even lower. Each wafer costs 40 to 50% more due to quadruple patterning, which requires 3 to 4 exposures per layer and consumes far more cleanroom time and materials. However, these metrics are irrelevant for military procurement. A guidance chip for a hypersonic missile might cost China several $100s instead of $50, but the missile itself costs millions. The PLA absorbs the yield tax because the alternative, relying on foreign chips that could be cut off in a crisis, is strategically unacceptable. State subsidies from the 3 phases of the Big Fund, totaling roughly $95 to $120 billion, keep the fabs running regardless of margin. In September 2025, the Financial Times reported that SMIC had begun testing a domestically built DUV immersion lithography tool from Shanghai Yuliangsheng Technology, a startup linked to Huawei's SAQP consortium. The project, internally codenamed Mount Everest, aims to replicate the capabilities of ASML 2008-era TwinScan NXT 1950i, a 193 nanometers immersion scanner that achieves 28 nanometers baseline resolution. With quadruple patterning, the same tool can be pushed to print 7 nanometer circuits, and possibly 5 nanometers at lower yields. The machine is not yet ready for high-volume manufacturing. Experts estimate that at least 2 years of refinement will be needed before it can be integrated into production lines. Still, the fact that a prototype is running inside SMIC test bays signals that China is systematically eliminating foreign touchpoints from its most critical lithography step. China already has a multi-pronged strategy to secure DUV lithography without relying on future ASML exports. Older ASML scanners purchased before 2022 remain operational and are being aggressively maintained, and Chinese fabs have stockpiled spare parts through intermediary channels. Simultaneously, Shanghai Microelectronics Equipment is working to qualify its own 28 nanometers ARF immersion scanner, while NARA and other domestic suppliers focus on etching, deposition, and cleaning tools to surround the lithography core. The combination of these efforts means that even if the US extends export controls to cover all DUV immersion equipment, China can keep its 7 nanometers lines running. The cost and throughput will never match TSMC EUV-based fabs, but for military-grade silicon, good enough is enough. According to open-source defense analysts and Chinese media reports, several PLA systems are increasingly incorporating domestic silicon, though specific node details are rarely confirmed by the military. The Chengdu J-20 stealth fighter AESA radar has integrated domestic silicon carbide semiconductors, reportedly improving detection range, and its mission computers are believed by analysts to use 7 nanometers class processors from SMIC. The DF-17 and DF-27 hypersonic glide vehicles are assessed to carry guidance chipsets fabricated on SMIC mature nodes, 28 nanometers or 14 nanometers, with newer variants possibly moving to 7 nanometers. The Type 055 Destroyer Combat Management System and the Winglong drone series are also cited as running on domestic chips, including Huawei Ascend accelerators for onboard AI. While no independent teardown has verified every node, the direction is unmistakable. Every new PLA weapons platform is being designed around a domestic semiconductor backbone. Western defense analysts often conflate consumer electronics, need for 3 nanometers chips with military requirements. In reality, hypersonic missile guidance needs roughly 1 to 10 gigaflops of computing power, easily handled by 28 nanometers or 14 nanometers logic. Fighter jet AESA radar signal processing depends more on gallium nitride transmit/receive modules than on transistor density, and 14 nanometers chips are more than adequate for beamforming algorithms. Drone swarm AI inference typically requires 1 to 10 trillion operations per second per node, which 7 nanometers accelerators like the Huawei Ascend 310P deliver at just a few watts. China's 14 nanometers yield is described as approaching TSMC level by domestic sources, and its 7 nanometers, despite lower yields, already meets every military requirement for onboard AI, sensor fusion, and autonomous targeting. The node race is over for weapons. China is already in the good enough zone. Huawei Ascend family has become the PLA workhorse for artificial intelligence at the tactical edge. The Ascend 910C, fabricated on SMIC 7 nanometers N+2 process, delivers roughly 256 teraflops of FP16 performance and is already being used for training drone swarm reinforcement learning models and electronic warfare signal classification. According to multiple supply chain reports, Huawei plans to manufacture 600,000 units of the Ascend 910C in 2026, nearly double the 2025 volume. A more advanced chip, referred to in industry sources as the Ascend 950PR, has been described as targeting 5 nanometers class performance, but its specifications and shipment volumes have not been officially confirmed by Huawei. Total Ascend die shipments across all models are expected to reach 1.6 million in 2026, creating a domestic AI hardware reserve that no longer depends on NVIDIA or TSMC. Hardware sovereignty is meaningless if the operating system remains vulnerable to Western backdoors or remote kill switches. Beijing has therefore orchestrated a systematic migration away from Microsoft Windows across government, state-owned enterprises, and the military. Kylin OS, originally developed by the National University of Defense Technology, now runs on more than 16 million devices in China. Critical infrastructure, including space missions with over 100,000 fault-free operating hours. The latest version, Neo Kylin version 11, is built on a hardened Linux 6.6 kernel and supports 8 domestic CPU architectures, including Lungsun and Phytium. Meanwhile, Huawei's HarmonyOS Next has removed all Android code and is being deployed on dual-use tablets and logistics terminals within PLA support units. While legacy Windows systems may still exist in back offices, all frontline C4, ISR, and weapons control systems have transitioned to domestic software stacks. Electronic design automation remains one of the most stubborn gaps in China's parallel ecosystem. Western firms Synopsys, Cadence, and Siemens control roughly 74% of the global EDA market, and their advanced digital design flows for 7 nanometers and below are not legally available in China. However, Beijing has poured resources into homegrown alternatives. Empyrean Technology now offers a full-process analog and mixed-signal EDA platform that supports 7 nanometers physical verification and has been validated by Huawei for 14 nanometers designs. Huawei itself claims to have developed a complete domestic EDA toolchain for 14 nanometers chips in partnership with local software houses. For complex digital system-on-chip designs at 7 nanometers, China still relies on pre-sanctions licensed copies of Western tools, but the gap is closing. The PLA can already design and tape out custom ASIC for missile guidance and radar processing without touching a Western server. While China builds a self-sufficient military chip ecosystem, the United States remains dangerously tethered to a single offshore foundry. TSMC in Taiwan produces the vast majority of the world's advanced logic chips below 7 nanometers, and the Department of Defense has acknowledged that critical weapon systems depend on these Taiwanese fabricated semiconductors. The F-35 radar processor, electronic warfare suite, and mission computer rely on 16 nanometers and 7 nanometers chips that are made in TSMC Hsinchu and Tainan fabs. The HIMARS fire control system, Javelin guidance logic, and Virginia-class submarine sonar processors all use chipsets that either originate in Taiwan or are assembled from TSMC-manufactured dies. If a blockade or conflict halts wafer shipments across the Taiwan Strait, the U.S. would face a catastrophic depletion of precision-guided munitions within weeks, not months. The United States has attempted to mitigate this vulnerability through the CHIPS Act and the creation of domestic crusted foundries, but progress remains far too slow. Intel 18A fab in Arizona is ramping production but is focused primarily on commercial customers, and GlobalFoundries operates only mature 12 nanometers and 14 nanometers lines. TSMC Arizona plant began 4 nanometers production in 2025, but it is not yet certified for defense-grade radiation-hardened chips, and its capacity is a tiny fraction of TSMC Taiwan's output. CSIS Wargames conducted in recent years have consistently found that a Taiwan contingency would deplete U.S. long-range munitions in days and take years to replenish, with chip supply disruption as a major compounding factor. The Department of Defense's own industrial base assessments warn that the majority of advanced chip supply for U.S. weapons flows through Taiwan, a single point of failure that China has already eliminated from its own arsenal. The most alarming trend for the Pentagon is not China's current capabilities, but the velocity of improvement. Each year since 2022, SMIC has delivered a measurable advance, from the first 7 nanometers Kirin 9000s in 2023 to the 5 nanometers N+3 pilot in 2024, and from low yields in early 2025 to a steady ramp in usable wafers by the end of that year. With every iteration, PLA weapons gain new abilities: longer radar detection ranges, faster electronic warfare response, denser drone swarms, and more accurate hypersonic terminal guidance. The United States, by contrast, remains trapped in a decade-long reshoring timeline while its forward-deployed forces continue to fly and sail on Taiwanese silicon. China has stopped playing on the Western board. It built its own, and its weapons are getting deadlier every year. The Pentagon cannot stop this curve because the tools to do so, export controls on DUV, sanctions on lithography, denial of EDA, have already been deployed and failed. The window for prevention closed in 2023. What remains is only management of an unstoppable technological divergence.